I have a conductor here. Because it's a conductor, the electrons will move freely. So what I'm going to do is I'm going to throw a whole bunch of electrons, excess electrons right here. So it already was balanced, and I just threw a bunch of electrons right here. What's going to happen? Well, from a force point of view, the electrons are going to start pushing against each other, and the electrons are going to start to spread out. They're going to keep spreading out until it reaches some sort of equilibrium, some electrostatic equilibrium. Well, if we think about that, if we think about an electron's going to move as long as it's exposed to an electric field. If I have an electric field here and I throw an electron into it, the electron's going to be forced in the opposite direction. So the electrons are going to keep moving until it's in electrostatic equilibrium, until the force in general, on average, is equal to 0 on the electron. And the reason why I differentiate equilibrium from electrostatic equilibrium is that these particles are still going to be moving around and bouncing around. There's some vibrations that are constantly going on. And so this is, electrostatic equilibrium is, on average, they're not moving significantly. And so these electrons will spread out. And so as long as there is an electric field in the middle, so if the electric field in the middle is not 0, that means that the electrons are still being pushed or pulled. And so they're going to keep spreading out, and eventually the electric field in the middle is 0. And so we can now make the claim that a conductor in electrostatic equilibrium has the electric field equal to 0 internally. This becomes a nice little thing to take advantage of.